I've written a 3D graphics library for the ZX81. Here you can see all the files that are in it. I'm using the same setup as I did for my previous video with the files from Byte Forever's method. And also you can see a couple of libraries. Xline lib2 is the main graphics library, and I've got some math routine for sine and multiply. So we've got demos from 1 to 16 to show the variety of features. Let's take a look inside Xline lib. First thing to note is we've got a buffer here that is the screen buffer. So this is a buffered system, which means that I'm plotting to the buffer first, and then I will transfer that buffer to the screen. That's why it's flicker free. And we can do this on the ZX81 because the screen is only about 500 bytes or so. And so, it's 32 times 24. The heart of the system is the line drawing. And that's done by this Bresenham line algorithm that you can find on Wikipedia, and I've left the link in there. The basic Bresenham line algorithm will draw a line that's no more than 45 degrees steep, and generally will only plot a line like that just going upwards at less than 45 degrees. So you need one line for going upwards, one line algorithm for going downwards, and another one for going steep, and then others for going in the opposite direction. So it's basically just one routine flipped in a variety of ways. That routine itself has to plot. And plotting on the ZX81 isn't that simple, because you've got to choose you've got to translate your pixel into both what character is that pixel going to be plotted in, and then how are you going to alter that character, because you don't have access to plot individual pixels. You've got to find a character and then translate that character into the one you want. So the way I've done it here to make it as fast as I can is to treat it as if I was just plotting normally into a 2x2 bit shape, and then have a value for that, translate that into a character value, and then another routine to translate from a value back to characters. So here we can see the problem that we've got is that the character code for the pixels that we want, they run logically up till 7. So top left is a 1, top right is a 2, both top ones is binary 3, bottom left is 4, then it's 4 plus binary 1, and so on. But when we get to 7, the way to plot them is now to plot the inverse video. And so here we can see the codes for the inverse video, and these run, unfortunately, in reverse. So character 128 is everything filled, so that would be binary 8 plus 4 plus 2 plus 1, so 15, and then 14, 13, 12, which is 4 and 2, and so on. So we just need to translate those in. There's a couple of ways of translating it. I've chosen quite a slow way, but I think I can speed it up with a faster way later. So here's the slow way that I've done it at the moment. The values that we'll have when we're plotting a pixel are going to be 0 to 15. So if the value is less than 8, then the character code is the value. But if the value of the pixels is greater than 8, then the character code is 128 plus the value minus 15. The faster way of doing that would be with ANDing and ORing. So there are those two routines. You find that there's routines written as normal routines and then fast routines. because after I'd written it, I tried to optimize it. I didn't really manage to optimize it very much, maximum of about 25% speed up. So I'd actually written it okay to start with. So you'll find that with all the clear screen, there'll be a clear screen and a clear screen fast. I also wrote some routines called clear screen Q fast or transfer buffer Q. The Q just stands for quiet, meaning that I'm protecting some of the buffers, some of the registers in the Q ones. So it should be protected really, but I put quiet. It's usually B, C, and D, because HL is usually corrupted by most things. So you can see that the Q just protects the registers and then calls the normal routine. Oh, a few delays in there. This delay, you load A with the length of the 1 byte length of the delay you want, and then call delay 2. Calc line is the main routine that takes 2 points, calculates the line between them, and decides what line plotting routine is needed. So you can see here it calls is line steep, and is line to steep decides whether it just needs a shallow line or a steep line. The calc line routine also decides whether it's a left to right or a right to left routine and swaps registers appropriately. Calc line safe checks for 0 length lines and then just doesn't plot them, doesn't plot a point. So if you want to plot a point, just plot the point directly with plot. Plot plots a point that you give it in the B and C registers. That's your Y and X. This is probably a good time to mention a good book that you can use if you want to learn machine code or improve your machine code. So this is a book from the 80s by Tony Baker. It's really excellent, very easy to read, and it's got some good examples. It tells you where to save your machine code in a basic program. It's great. So the ZX81 primarily works in BASIC, and of course we can plot lines in BASIC using the plot XY command, though it won't surprise anybody that it's not the fastest thing, and that's just really plotting a very basic line. Okay, now I'm going to quickly go through all the different demos that we've got. So, demo 1. Demo 1 just plots some lines. So the draw shape, and then it calls the resonum line in the library. And this has a PC loop to alter the X coordinate in the C register. Demo 2 calls this routine show point. So you just set the X and Y coordinates for the line, then call the show point. It's worth noting at this stage that right after the start of your program, you need to call X line init, which just sets up a few. See if I can find it. Yeah, X line init. So it just loads HL with the address of the buffer, which is where you're going to plot to. So you tell it where to plot, and then later it transfers that to the f_cc, which is the start of the screen memory on the ZX81. Okay, that's demo 1. Demo 2 is just plotting some points and then drawing the line. Notice that we call clear Q, that clears the buffer, not the screen, it clears the buffer. So we clear the buffer, the screen stays the same. We do all our plotting to the buffer, and then we call transfer buffer, which transfers the buffer to the screen memory. And that's why there's no flicker. And then here you see the delay. So load a value into the A register and then call delay. If I wanted a shorter delay, I'd change it to say 1F or whatever. Okay, that's demo 2. Demo 3, plotting a circle. So I mentioned X line in it. Also worth mentioning that after line 1, the first thing in your program must be this jump to demo start, because in line 1, well, line 1 is the rem statement. At the end of your program, you've got line 2, and what line 2 is doing is rand user and then 16504, probably with 16514, and that has to be this address. Otherwise, it would be calling into the middle of the data, for example, or into the middle of one of these files. So this must be the first one, and then you jump to where your program starts, demo start, and that means you can have all sorts of data here if you want to, because it's not going to jump into it. There's no danger of it jumping into it. A nice thing about this routine is it uses one of the routines from Brandon's library. See if I can find it. Is it calling the sine and cos? When it calls the sine, it calls it with an angle. That's in here. And then if you add 90 to that angle, you get the cosine, because cosines are 90 degrees out of angle. So there's me calling the cosine of an angle. There's me calling the multiplication routine. Yeah, here's the display. So what disp_HL does is it displays HL on the screen. That's what these two numbers are. I think these are the sine and the cosine times the length of the radius. I think I've got radius as one of the variables somewhere. Oh no, it's hardwired in this one. Later I have radius as a variable. All right, it's demo 3. It's just running the plot without delays. Demo 5, same thing, but this time instead of plotting individual points, it's going to call calc line, I think. Yeah, here we go. So instead of plotting the points, it calls calc line. It needs, therefore, to have a last point, that it plots from the last point to the current point. And it uses the exx command to store in the B register of the shadow registers that to tell it don't draw the first line. I like this one, number 6. So it's just drawing a circle again, but this time it uses this variable radius, which is just a radius in the x direction. So it slowly makes the radius larger in the x direction. Radius. Yeah, in the circle loop, it uses the radius and then multiplies the where it was going to plot the point by the radius. Okay, demo 7. Obviously I'm thinking of Elite, and I'm trying to simulate a globe. Elite draws a small circle that moves across the globe, but I've done this one by taking half a circle and then just compressing it with the same trick that we saw in the last routine. And it makes it look like it's not actually 3D, but it makes it look like 3D. Demo 8 is the first one where I've got this connections idea. So this is really, it should be edges, but I started with connections and it's just stuck. So I've got 4 points, and the connection just says connect point 0 to point 1, point 1 to point 2. So if I was to say connect 0 to point 2 as well, then you wouldn't get a square anymore. Same thing, but just rotating it now. Because I'm rotating it, I need 2 arrays. One to store, I've got it point safe, so that's to store the initial values, and then one to store them in as I rotate it for different angles. Noting connections, there's an FF at the end to tell it that it's reached the end of the edges. So you've got an angle that you're going to start at, and then it's going to rotate. Points to rotate, I created this variable to say where am I taking my points from, and then points to save, where am I going to save the point. It's kind of the way you do arrays, I guess, in assembler. Number 10. Oh, now we're getting to fun. So this is just the same as drawing lots of points, except that you can have a Z component as well. Obviously you don't plot the Z component, but as you rotate them, the X and the Y components drift into the Z component and drift back again as we rotate. More connections this time, because you've got connections between the 4 corners of the 2 squares. It's pretty much the same as before. I had an angle and an angle cos this time because you've got to, it's a new x is sine of the old x plus cos of the new x. No, sine of x1 plus cos of y1. I just need more places to store everything. Demo 11's missing because it was boring. Okay, now we're getting towards the fun. Demo 12. This is a Viper from Elite. So pretty much the same, just with a new model. Not much to add, really. It was worth noting at this point because this is a slightly larger model. And I'll show you the Python. I've grabbed this from the Python files. I wrote a Python script to grab it, from the assembler for the BBC Micro version of Elite. So you can grab the models straight from there. In the repo on GitHub, I've included a Python script that is really going to be quite useful because it allows you to generate the model. At the beginning of the assembler demo, there are a few sections called points, faces, points safe, faces safe, points temp, faces temp, Connections, edge faces. So apologies for the name, but here's what they all are. The points are what are often called vertices for your model. The faces are really the normals of the faces. So this is what we can use to decide whether to hide the edges or not, whether they're visible or not. I'll come to those a little bit later. Each set of these forms the points, if you like, that we will rotate. And because we, in general, want to do a couple of rotations, we'll start with the original set of coordinates, then rotate by one angle, and then rotate by another angle. We need a couple of arrays to work in, and that's what points safe and points temp are. This is currently the results from one rotation, and then this is rotated in another angle to form the final points that you will plot. Given a BBC Micro file taken directly out of the Elite code, which I'll show you in a bit, this program will translate it. If I run it, module, I'll give you a visual of what you're seeing. This is the Coriolis space station, and it gives you the output that you just need to copy and paste. It gives you the work arrays, the coordinates, the edges, the faces, and it also tells you the number of points and faces together, which together are the number of things that you need to rotate. And in the code you'll find a line. I'll show it to you. Yeah, here, just after the start. So you replace these, and you replace this line, and that's all you need. This code at current doesn't check whether you're plotting inside the boundaries of the screen. If you plot outside the screen, you will probably corrupt the memory. If you plot over the edge of the screen, you'll corrupt the new line character, and the screen will go wonky. If you plot earlier in memory by going too far up this way, you'll overwrite the system variables, and your program will crash. If you overwrite this way, there's a chance you might get away with it, because I think this basic variables are there, but it's still not a great thing to do. So that's why I've written the Python script, just to make sure that the model is scaled so that when you rotate it, it won't go off the edge of the screen. Later I need to write a check so that we can have models going off the screen, but one thing at a time. This one was just slightly off center. So now I need 3 arrays. One to do a small rotation in one direction, and then the same as normal from point safe to points to do the final rotation. So we take the original coordinates, rotate them slightly off, and then keep on rotating them into the final one. So I always see, I think I've done a 45-degree angle. Yeah, you can kind of see that's 45 degrees. Just to set up my initial model. And then I just do the rotations as normal. And here are 2 rotations, one in one direction, one in the other direction. I do a bit of a trick here, which you can see by this increment HL. So normally it would load into HL the points to rotate, and that would give you the columns X and Y of points, and you would do a rotation on those 2 columns. But by incrementing by 1 HL, I flip over onto the Y and Z columns. It's a bit of a dirty trick, a bit of a hack, because by doing that, I don't leave myself an easy way to move to the Y and the X for the final degree of rotation. But it was just an easy way to make a more interesting demo. And so later it needs to be corrected, really write a better piece of code. Because I've got a double buffer, I can put the circle into the buffer first and then write the spaceship, the Viper, over the circle. And then the buffer is cleared. And then I can write the same things again. So it allows you to draw one shape over another shape, and it doesn't delete it. It doesn't delete it because we're never deleting the shape, we're just wiping the whole buffer. And the time it takes to wipe the buffer and transfer the buffer, even though it's having to transfer all this empty space as well, is so much less than the time it takes to draw the model. I think each line of the model takes as much time as it does to clear the buffer and to transfer the buffer. So we could have the rotating Earth behind the ship, and that would just be as easy to draw as the ship on its own, really. You can see it's a little bit slower because it's drawing the Earth and the ship as well, but it's still manageable. And then finally, the one I was kind of pleased with. So this is the removes the lines you can't see, which it does by introducing a new component, if you like, which is this idea of faces. So these are the normals to the faces. So that's a face there. It will have a normal pointing outwards. And so when that normal is pointing in the negative z direction, like this one is, then that face is hidden. If that face is hidden, then the edge, if an edge lies on two hidden faces, then we can't see that edge. So that's the trick here. The faces and the normals were included, as well as the these, I've called them edge faces, but these are the, for each face, there are two edges. These were included in the BBC Elite program, so this must have been the way that they did it as well. It's quite quick to do. It's just a matter of saying, what's my edge? What are the two faces? Loop through the faces on the edge, and then just check that those faces both are visible when they're rotated. And this trick I've done here means I don't have to write any more code to do the rotation of the faces as well. It just does them at the same time as it does the edges, the vertices, the points. And then all I have to do is to make sure that I make the number of points to rotate large enough to include all the points and the faces as well, the normal faces, normals. And that's it. And then we're back up to the start, which is the Coriolis space station, which is exactly the same code, just with a different model in. So a shout out for a Mark Moxon, who's done a disassembly of the Elite. So if we go to his GitHub repo, which I'll put the link below, source files, main sources, Elite source, and right at the end of here, it's got all the models. So this is the format that I've used in my Python script. It just searches for the vertexes, and that's got the X, Y, and Z. I've not used the face information. Here it's got the edges, and so I've used the I've called these connections, and then I've used the faces. So every edge obviously is on two faces, and then it's got the normals to the faces down here. So I've used those three parts. So any file that you've got that uses those three parts, you can just put straight into the Python script, and that will produce the format that you need for the assembler. Just basically rearranging it. So I found this useful resource for coding in Z80 assembler. Brandon Wilson seems to be one of the key contributors. So he's got some information on optimizing your Z80 code, including these really useful multiplication routines. So I've used this one. Multiplies h by e and places the result in HL. Well, there's a whole load of other ones as well for different sizes and signed. I should maybe have used this signed one, but I didn't. I just used the basic one.